Okay, so what we're going to go over today is just kind of the notes for balancing. I know you guys already know how to do that. We've been doing it already for like a week. Okay, but I just want to kind of go over the formal notes for balancing. That won't take us very long because, like I say, you guys already know how to do that. Okay, and then we're going to look at how do I predict the products of a chemical reaction. All right, so we need to first off understand that the amount of atoms on the reactant side of a reaction or equation must be the same as on the product side. That's the law of conservation of mass. It is the reason why we balance chemical reactions. Okay, need to learn to use coefficients to balance equations. We already know how to do that, but this is just a quick review. Okay, and understand that obviously matter cannot be created or destroyed. That's important when you're predicting the products of a reaction. Okay, remember what Dalton said happens in a chemical reaction. Atoms can be separated, joined, or rearranged, but not turned into other atoms. Okay, so when you predict the products of a reaction, if all you have on the reactant side is potassium and chlorine and oxygen, you better not have lead on the product side, because you can't do that. Okay, that would be creating something from something you didn't have. All right, so we have to remember that. Okay, so law of conservation of mass says that mass must always be conserved in reactions because matter can't be created or destroyed. All matter has mass, so the mass of the reactants must equal the mass of the products. That is always true. Okay? For a long time, people did not believe that that was true, especially in reactions that produced gases. Okay? Because they would not contain the gases, they would simply float away, and the mass of their reactants would not be the same as the mass of their products. Okay? If we contain everything, then it will always be the same before and after, because for it to change would mean that atoms, matter, actually physically disappeared, or appeared out of nowhere if suddenly the mass got bigger. All right? So we have to remember that in all reactions, okay, everything has mass, even gases. Okay? Some people have trouble getting their head around the fact that gases have mass. Okay? The stuff you're breathing in right now has mass. Okay? It's why there's atmospheric pressure. The weight of all of that gas being pulled down by gravity onto you exerts atmospheric pressure. Okay? That's all there. Pick up like a flat tire. Okay? Like it'd have to be a car tire. It'd have to have a significant amount of air in it. Okay? But if you picked up a tire that was not inflated on a rim and then picked it up after you inflated it, it's going to be noticeably heavier. Okay? The amount of gas you would put in that tire would be noticeable, okay, in terms of a change in weight. Okay, so just looking at the example here, we've looked at this reaction time and time again. Okay, if I take two hydrogen molecules and react it with one molecule of oxygen, I will get 2 molecules of water. Okay, but I have 4 hydrogens and 2 oxygens on both sides. I have conserved mass, conserved matter by balancing the reaction. Okay, questions on balancing? Balancing doesn't seem to be giving you guys too much trouble from what I've seen. All right, so in the law of conservation of mass, obviously in any physical or chemical change, total mass of the starting materials must equal the total mass of the product materials. On your unit exam, there's almost always a multiple choice question about the law of conservation of mass. It might be worth your while just to know that one, okay, so that you can correctly identify it on the test. All right, box A is my reactants. Which box below that correctly shows the law of conservation of mass obeyed? D? Yeah, I think so. Okay, so we got 6 8s. We've got 8 yellows. Okay, and there's 1, 2, 3, 4, 5, 6, 7, 8 yellows. Okay, in D, and we've got 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Yeah, so definitely D. I mean, it's obviously not C. Okay, we can clearly see in C there's just not enough matter there. Okay, and obviously in B there's not enough of the yellow ones, okay, in there. All right. So if we're balancing a chemical equation, okay, and I'm just going to quickly go through this, okay, our rules for non-combustion reactions start with the biggest number, okay, and balance back and forth from there. Okay, that's really all you need to remember. And then for combustion reactions, we have the 2 rules, balance alphabetically and the rule of 2. Okay, you guys are already familiar with those, so we're going to skip right over this because we've already done that. All right, predicting reactions. Okay, so there's a set of steps to go through to predict the products of a chemical reaction. You might want to write these down. Okay, step number 1 to predicting a chemical reaction. is to identify the reaction type. Okay, that's step number 1. So if I'm looking at the first reaction here, where I have calcium reacting with oxygen, what kind of reaction am I looking at? It's a synthesis reaction. We only have one reaction type that starts out with 2 elements reacting with each other, and it's synthesis. Okay? So now that I've identified this as a synthesis reaction, I have to know all of my reaction patterns. Okay? In a synthesis reaction, these 2 elements are going to combine. Okay? That's one of the things Dalton said could happen in a reaction. Okay? They can join. And he also said they would join in simple whole number ratios. Right? So when I put these 2 together, I'm going to get an ionic compound, because calcium is a metal, and oxygen is the non-metal. Once I make an ionic compound, what do I need to do with it? I need to balance the charges. In other words, I need to do the drop and swap and make sure I have it written correctly, because if I don't, I'll never make this balance. Okay? So, calcium is a 2+, oxygen is a 2-, so those already cancel each other out. The ratio is 1 to 1. Okay, on that. What's the last thing I need to do with this reaction? Balance it. Okay? My calciums already look good, but my oxygens do not. There's 2 oxygens in the reactants. Now there are 2 in the products, but that gives me 2 calciums. I go back over here, I've got 2 calciums. I'm done. That's all there is to it. It really isn't any different than just writing the reactions. Okay? You still need to be able to identify them. The only difference is you have to know the patterns well enough to put it together. Okay? All right. What reaction type would number 2 be? Decomp reaction. We only have one reaction type that starts out with a single reactant. Okay? And it's decomposition. What happens in a decomposition reaction? They're separated, right? Okay? According to Dalton, these ones are separated. So they're going to separate into their 2 elements. Anytime I produce elements, especially non-metal elements, what do I need to check them for? If they're polyatomic or special. Okay? So magnesium is a metal. There are no special metals. Okay? But sulfur is special. Okay? And it comes as an 8. Okay? So that's another thing. We always have to be mindful of that. When we're predicting reactions, there's lots of things to check. Okay? Now what do I need to do with this? Just balance it, right? Okay? Not balance. Start with the biggest number / only number. Okay? And make this thing work. Okay, number 3 is the easiest kind to balance, because it doesn't matter what these 2 numbers are. The products will always be what? Carbon dioxide and water. All combustion reactions produce carbon dioxide and water. Okay, it isn't something you have to think about. Okay, if you see carbon, hydrogen, oxygen, CO2 and water on the other side of the arrow each and every time. Okay, it's not one you have to think about. Okay. What do we do now? Okay, do I need both rules? No. Okay, so 3 carbons. Okay, there's 8 hydrogens. So a 4 here will give me my 8 hydrogens. 3 times 2 is 6, plus 4 more is 10. 5 times 2 is 10. Try the 4th. Okay, so remember, steps are identify the reaction type. Use that pattern to predict the products. Check for specials. Swap and drop. Balance the reaction. Okay. So, what kind of reaction is this? Double replacements. 2 ionic compounds, that's the only reaction type we have that starts that way. Okay. If I have a double replacement reaction, what do we say always happens in a double replacement reaction? We just switch the metals, okay? That's our pattern. As long as we know the patterns, it's very easy to predict what will be on the other side of the arrow. So hydrogen and sodium are going to switch partners, which means that hydrogen will end up with hydroxide and sodium will end up with chlorine. Okay? Simple as that. Okay, I have my product. And my reaction is already balanced, so I don't need to do anything there. All right, now, the one reaction type that's probably got the most to do is this type, is the one I didn't have on here. Let's see. What reaction type is that? Single replacement reaction. Okay, in a single replacement reaction, obviously there's going to be a rearrangement of the atoms. Okay, so what I have to do is I have to look at what my element is, and it needs to replace the part of the ionic compound that is like it, or similar to it, or the same. Okay, so chlorine is a non-metal, which means it's going to replace sulfur. All right, so sodium is going to now be with chlorine, and sulfur is going to wind up alone. Okay? Once I've predicted the products, now I have to check for drop and swaps and special elements. In a single replacement reaction, you have the most to check for. Okay? In any of the other ones, you might have to drop and swap. You might get a special element produced or something like that. In this one, you always have both. You have an ionic compound that will have to be dropped and swapped, and you'll have an element that could possibly be special, right? So you always have to be checking for that stuff in a single replacement reaction. Okay, sodium's a +1, chlorine's a -1. That compound is swapped and dropped, all right. Sulfur, special? Yes. Okay, now I need to balance this reaction. Okay, I have 8 sulfur on this side. Start with the biggest number. Now I have 8 over here. That gives me 16 sodiums. So I need to go here and make sure that I have 16 sodiums. That gives me 16 chlorines. So I need to make sure I have 16 chlorines over there. Okay? All right. Steps, once again. Identify the reaction type. Use the pattern to predict the products. Swap and drop any ionic compounds. Check for special elements. Balance the reaction. 5 steps. Okay? You do those 5 steps on every reaction, you can't go wrong. Okay. All right. So I built this flow chart. I'll put it in Google Classroom if you want it, but it's basically what I just did, except it's more complex. Okay? It's actually specified for each type. Okay? But very simply, those 5 steps I just gave you will work all the time. Okay, skip over that. All right, I want you guys to try these ones here. Okay, so there's 6 there. Let's just do the first 3 for right now. All right, so I want you to write those ones down, predict the products for me, and balance them. For number 5, okay, I've got beryllium reacting with iodine. So 2 elements reacting means this is a synthesis reaction, right? In a synthesis reaction, the 2 elements are going to be joined, okay, into, in this case, an ionic compound. All right, I have to look at the charges because I'm making an ionic compound, so I have to make sure it's dropped and swapped correctly. Okay, iodine's a -1, beryllium's a +2, so we're looking at BeI2 as my product for that one. Okay, and that means then that the reaction is already balanced. How many people have done number 6? Let's have a look at that one too then. All right, so in number 6, I have potassium as an element. It's a metal, and it's reacting with iron 2 oxide. Why is it important for me to know which iron it is?
Because when the iron...
It's a trick question. Yes, it's a trick question. Actually, in this question, it doesn't matter because iron's going to end up by itself. It would matter if it was a double replacement reaction and you had to match up iron with something else on the other side and drop and swap. Then it would matter. Okay? And there are rare situations where the following could happen. Okay? Let's say I have this reaction. Copper reacts with sodium chloride. And that's going to produce sodium plus copper and chlorine. What do? Copper has more than one charge. On this side where I started, it was an element and had no charge. How do I know which charge to use in this situation? Well, I can look there, but the problem is that I'm trying to drop and swap this compound. I do know that chlorine is a -1, but I don't know what the charge on copper is to do that drop and swap. I'm the one who has to decide what the number that goes on chlorine is here. Okay? So, here's the answer to that. Whatever charge is listed first, left to right, is the most common charge for that metal. And in this situation, that's what you have to go with. Okay? Because in reality, the most common charge is the charge that happens 99% of the time. Okay? The other charge is a much smaller occurrence. Okay? So for copper, the more common charge is 2, right? Yeah. Okay? So this would be the 2 plus copper would be CuCl2. All right, so that's a rare case. That can happen. Okay? Didn't happen obviously in this particular reaction, but it can come up. All right, this is a single replacement reaction. The metal is going to replace the metal. So iron is going to end up alone. Potassium will end up with oxygen. Iron's not special, so it doesn't need any numbers, but I'm checking it anyway. Okay, and oxygen's a -2, potassium's a +1. Because I'm making an ionic compound, I need to make sure that I drop and swap, and now I can balance. All right, got 2 potassiums on that side. Now I've got 2 potassiums on this side. That would be fine. It makes no difference whatsoever. Yeah, okay, that's a good question. Okay, I could have just as easily written it like this. That would be equally correct. Okay, either way will work. All right, how many people have done 7? Okay, let's have a look at that one too then. All right, so on number 7, here's that situation again. I've got copper with sulfate. Okay, sulfate's always a -2, so this is the copper with which charge? 2. All right, so I'm going to need that on the other side because this is a what kind of reaction? Double replacement. All right, that means copper is going to end up with chlorine and magnesium is going to end up with sulfate. Okay, I've just made 2 new ionic compounds. Both will need to be dropped and swapped. Chlorine's always a -1, and I figured out over on this side that copper was a +2. Okay, so that means this is CuCl2. Okay, and then this stuff is -2, this stuff is +2, so it's fine. The way it's written, it's just MgSO4. Now I need to balance. Done. Okay, that one's already balanced. Okay, just making some sense? It's really not a lot different than what we were doing last week. All right, have you do the other 3 here. Combustion reaction. Okay, so what are always the products of a combustion reaction? CO2 and water, right? There's nothing to kind of figure out on this one. That's just memorization. Whenever I have a combustion reaction, those are my products. Okay, now I need to balance it. Do I need both balancing rules here? Yes, 4 is an even number. All right, so I need to start with a 2. 2 times 4 is 8. So now I have 8 carbons on the product side. 2 times 10 hydrogens is 20. 10 times 2 hydrogens is 20. Now I got to look at my oxygens. 8 times 2 is 16, plus 10 more is 26. 13 times 2 is 26. Okay, now my reaction's balanced. Questions on number 8? Okay, how many people have done number 9? Okay. What kind of reaction is number 9? The decomposition reaction. It only has one reactant, so it has to be a decomposition reaction, which means it's going to break down into rubidium and phosphorus. Okay, in a decomposition reaction, I'm making elements. What do I need to check them for? If they're special or not. Rubidium is not, but phosphorus is. And so it needs a 4. Okay. Now I've got to go back and balance. I'll start with phosphorus because it's the biggest number. I'll put a 4 here. Now my phosphorus are balanced. 4 times 3 is 12. 12 rubidiums on the product side, and now the reaction's balanced. Okay. Now people have done number 10. Okay. What kind of reaction is number 10? Double replacement. What do we do in a double replacement reaction? Switch the metals. Okay, so I'm going to have lead is going to end up with phosphate. Okay, and cobalt is going to end up with chlorine. Okay, I'm making 2 new ionic compounds. What do I need to do with both? Drop and swap. Both contain multivalent metals. This is as crazy as one of these would get. It has multivalent metals on both, polyatomic ions on one of them. Okay, it's madness. Okay, so I need to figure out what the charge on lead is over here. Well, chlorine's a -1 and there are 4 of them, so this is the lead that is 4 plus. All right, so I'm going to go over here. Phosphate always has a charge of -3. Okay, so if this is a -3 and this is a +4, I'm going to have a 3 come down here. I'm going to need to put brackets around the phosphate and put a 4 outside the brackets. All right, now swap and drop that one. Now I need to do the same thing with cobalt. Okay, phosphorus is always a -3, and there are 2 of them for a total of 6 negative charges. So that means I need to get 6 positives out of the cobalt, so each cobalt has a charge of 2. Okay, so this is a 2 plus, this is a 1 minus. I got COCl2. And now the craziness of balancing begins, because I've got lots of little numbers to contend with here. I would say probably my best bet would be to go with phosphorus. We'll give that a try and see how that goes. Okay, I've got 4 of the, phosphate over on the product side. I'm going to come back over here and make sure that I have 4 phosphates. Okay, when I do that, it gives me 6 cobalts on the reactant side. So I'm going to go over here and make sure that I have 6 cobalts. Okay, that gives me 12 chlorines. So I'm going to go back over here and make sure that I have 12 chlorines. And always a good sign, when I put that 3 there, it made the last thing in the reaction balance for me. Okay, I'm making 3 leads on both sides. Okay. All right, how are we feeling about that stuff? All right, I'm going to give you about a 3 or 4 minute break here, and then I'm going to put a few more for you to try up on the board here. So take a 3 or 4 minute break when you go to the bathroom, okay, answer your snaps, whatever. Okay, do that. Okay, so for our first one, all right, we've got potassium reacting with water, but written as OH. Okay. What kind of reaction is that? Single replacement. Okay, that's why water was written like an ionic compound and not as a molecular compound. Because if I wrote an H2O, do molecular compounds participate in these types of reactions? They do not. Okay, which is why I wrote it that way. Okay, so we're going to have hydrogen ending up by itself and potassium ending up with hydroxide. I've produced an ionic compound, so I need to drop and swap it. It's already good because they're both 1s. Okay, hydroxide's a -1 and potassium's a +1. Hydrogen, however, is special, so it comes as a 2. Okay, and that's one of the things I need to check for, especially in a single replacement reaction. That means now I need to put a 2 in front of water here, which will give me 2 hydroxides. So I've got to go over here and make sure I have 2 hydroxides, and then come back to the reactants and make sure I have 2 potassiums. Right, so the reaction should look like that instead.
So does that mean, depending on how you write it, water can be both ionic and
Yep,
compound?
that's exactly what I mean. Water's that thing that if there's a rule, water's the rebel. Okay, water is the exception to basically every rule we have. Okay. All right. Question number 2 here. I've got copper 1 sulfide. Okay, I know this is the copper with the 1 plus charge because sulfur's a 2. Okay, and reacting with sodium hydroxide. So what kind of reaction am I looking at there? Double replacement. They're both ionic compounds. So in a double replacement reaction, I swap the metals. That means that copper is going to end up with hydroxide and sodium is going to end up with sulfur. Okay, I've just produced 2 ionic compounds. What do I need to check them for? Charges. Got to drop and swap. Okay, so I checked on the other side to figure out what the charge on copper was. Since sulfur is a -2, this copper must be the +1. So +1, -1, so that works. Okay, +1, -2, so I got to bring a 2 down here. And now my reaction is written correctly. Now I just need to balance it. Starting with the 2 over here, I'm going to come back over and make sure I have 2 sodiums on this side. That's going to give me 2 hydroxides. So I need to put a 2 there, which makes my copper work. And now my reaction is balanced. All right, if you guys can mask up and quickly give your desks a wash before the bell goes, that'd be awesome. Remember, guys, if this is giving you trouble, I'm available for help every day at lunch. Okay, I have no life. I'm always in here. Okay, come see me anytime.